Hi folks, today we're going to talk about something a little new and a little different. Our topic today is about something called an inverse. So our essential question, since we really don't know what an inverse is what is an inverse? So that's one of the things that we need to answer is what is an inverse? And then once we figure out what it is, we want to know how do you find the inverse of a table, of a graph, or of an equation? Okay, so those are our essential questions. What is an inverse, and how do you find the inverse of a table or equation? Well, an inverse is very closely related to an original relationship. So in example 1, I have a table of x and y values, and every x value has a certain relationship with y. That relationship is defined by whatever equation we can come up with that combines this x and y set of values. Now, in a table, in order to write the inverse, that means that you take the relationship between x and y and you kind of switch it around. So in a table, in order to find the inverse, you literally take the x values, they become your new y values, and you take your old y values, and they become your new x values. So you invert the x and y values. So instead of my x values being -2, -1, 0, 1, 2, 3, now my y values are -2, -1, 0, 1, 2, 3. And instead of my y values being -0.25, -5, 1, 2, 4, 8, those old y values are now my new x values. So I've just switched them around and created my inverse. There's still a relationship between x and y, but it's just inverted. Now, what I'd like to do is show you what that looks like on a graph. So first we're going to graph table 1. We're going to graph the original relationship, so original. When I graph that, I have the point -2, 0.25, so that's about a fourth. So -2, 0.25, about right there. -1, 0.5, about right there. 0, 1, so y-intercept, 1, 2, 2, 4, 1, 2, 3, 4, and 3, 8. 3, 1, 2, 3, 4, 5, 6, 7, 8. There we go. So this is the graph of the original relationship. So I'm going to go ahead and connect it with a curve. And I'm going to kind of show almost like an asymptote right there. Now the inverse is graphed like this. So -0.25, 0.25, -2. So 0.25, -2. 0.5, -1. 1, 0. 2, 1. 4, 2. And 8, 3. So 4, 5, 6, 7, 8, 1, 2, 3. So if I connect that with a curve, I notice that these two graphs look very similar. They both have the same shaped curve. They're just kind of going in different directions. And what you'll notice is that these two graphs are reflections of each other over the line y equals x. The line y equals x is this parent function, this linear parent function. It goes through the origin. It has a slope of 1. There we go. And when two graphs are reflections of each other over the line y equals x, then they are said to be inverses. of each other. To graph the inverses of an equation, all you need to do is switch x and y values and plot the new points. So we're going to start off our conversation about inverses with a very simple idea of just switching x and y values. For example, let's say we're given this set of ordered pairs, 2, 3, 4, 6, 8, 12. If I want to write the inverse of these 3 points in a set, well, the inverse is going to be a set also. And instead of 2, 3, what would I do with those? Well, I would switch x and y. So this would be 3, 2. That's the first inverted point that I have. Go ahead and write the other 2 points for the inverse. Check yours with mine. All we've done is we've taken the x and y values and we've switched them. Now, in example 3, it says given 2, 3, 4, 6, and 6, 3, so almost the same set of points, but this last one is a little different. We're asked, is this a function? So if I figure out if this is a function or not, well, my brain should be thinking about x values. And in a function, remember that x values don't repeat. So in a function, we have no repeat x values. Just a little review. No repeat x values. So let's look at the x's. We have a 2, we have a 4, we have a 6. Is this a function? Absolutely. There are no repeating x values. Now, the next part of example 3 asks me to write the inverse, just like we did up here. So we're going to write the set, and we're going to invert each point. 2, 3 becomes 3, 2. 4, 6 becomes 6, 4. And 6, 3 becomes 3, 6. Ending the set with a brace. Now the question that remains is the inverse a function? Is this a function? Well, again, I'm looking at x values. I don't want them to repeat. So I have a 3, I have a 6, and I have a 3. Is the inverse a function? No, the inverse is not a function. And the reason is because the x value of 3 repeats. So far, we're just taking the idea of an inverse and applying it to points where we switch the x and the y. Now, to find the equation for the inverse of a given relation, you're going to do something very similar. First of all, if your equation has f of x, well, f of x is the same thing as y, right? So we're going to change the f of x to a y. And what had we been doing on the first page to find the inverse? What did we do with x and y? We switched them. So we're going to do the same thing here. In order to find the inverse, switch x and y. And instead of having y equals, you'll now have x equals. Well, that's not what we want. So you need to solve your new equation for y. And if the inverse is a function, you can rewrite it as this. And the way you pronounce that is the inverse of f of x. This little kind of looks like to the power of -1. It's really not an exponent, but it means inverse. That's the way you denote an inverse. Now, if the inverse is not a function, it's still the inverse, but you can't include f of x because it's not an inverse. So you would write it like this, and it's read as the inverse of y. So you have to pay attention to your final inverse and determine if it's a function or not. And I'll show you how to do that in a moment. So let's look at number 4. It says write the equation for the inverse of each of the following relations and functions. So I need to write the equation for the inverse. That's my goal. So first step, I don't want f of x in there. I need to replace it with a what? With a y. So I'm going to rewrite y equals 4x plus 8. Next step to find the inverse, I take x and y and I switch them. So instead of y equals, I have x equals. Instead of 4x plus 8, I have 4y plus 8. In order to get the equation for the inverse, I need to solve for y, so I'm going to move my constant. 8 minus 8 disappears. I have x minus 8 equals 4y, and my last step is to divide by 4. So I have y equals, x over 4 is like 1/4 x, and negative 8 over 4 is negative 2. Now here's my inverse, but whenever I write it, I need to determine if it's a function or if it's not a function. Well, this looks an awful lot like y equals mx plus b, and that's kind of the normal form, that's the slope-intercept form of an equation of a line, of a function. So we would say that the function of f of x, the inverse of f of x equals 1/4 x minus 2, because this is a function. It's like f of x equals mx plus b. Okay, so I'm going to help guide you through the next one. The next one, it doesn't have f of x, it has a y already, so I don't have to replace f of x with y. But what do you need to do with x and y? You need to switch them. So pause your video and switch x and y. Make sure yours looks like mine. Now in order to get the inverse, you don't want x equals, you want y equals, so what do? You solve for y. So pause your video, move the constant, move the coefficient, and solve for y. Pause your video. So check your work with mine. We subtract 7 from both sides and divide everything by negative 5. We have that y is equal to negative 1/5 x plus 7/5. This again looks like mx plus b, a function that is linear. So I'm going to rewrite this as the inverse of f of x equals negative 1/5 x plus 7/5. Okay. So let's go on to number 6. Number 6, to find the inverse, what do I do with x and y? You switch them. So rewrite with them switched. You need to solve for y, so you move the constant. But this is a little different. So how do you unsquare y? Because you don't want y squared equals, you want y equals. So how do you get rid of the squared? What's the opposite? You square root. And what you do to one side, you do to the other. So we have y equals the square root of x plus 6. But when you take the square root, your answers are not just positive, they're positive and negative. So anytime you take the square root, your answer is plus or minus the square root of, and then whatever your radicand is. Now, to determine if this is a function or not, I'd like to call your attention to the graph that it creates. So I've gone ahead and I've typed into Desmos. There we go. I've gone ahead and typed into Desmos y equals positive square root of x plus 6 and y equals negative square root of x plus 6. And I have them as separate because Desmos doesn't allow me to put plus or minus and then graph it. So I just want to show you what they look like. Here's part of this graph, and here's the other part, of this graph. So together, these two pieces create a parabola that's opening horizontally. And so if I'm trying to determine if this is a function or not, well, I notice that maybe I type in x equals 2 or something like that. I notice that this parabola laying on its side does not pass the vertical line test. It touches a vertical line more than once, and so that means that this is not a function. So whenever we rewrite this as an inverse, we're going to just write it as the inverse of y equals plus or minus square root of x plus 6. And you'll notice that anytime you have plus or minus the square root of something, that it's not going to end up being a function because you end up getting a horizontal parabola that doesn't pass that vertical line test. Okay. Let's go to number 7. Number 7, I'm going to ask you to pause your video and try it out. Replace f of x with y, switch x and y, and solve for y. Pause your video and check back. So check your work on number 7. I feel confident that you could at least get through this step. So f of x becomes y and x switch places. You want to solve for y, so you move the constant. It's the next step that I feel like if you made a mistake, it might have happened here, or if you stopped because you didn't know how to proceed, it might have happened here. So if you're trying to get rid of this 3/8 that's being multiplied by y, well, the way that you undo multiplication of a fraction is you multiply by the reciprocal, the switch. So the reciprocal of 3/8 is 8/3. I do that on the left side as well. And I've got to do it to both terms. So 8/3 times x is 8/3 x. And 8/3 times -3 is -8, because the 3 and the 1/3 cancel out. So because this kind of mirrors a linear function, mx plus b, then we rename this as the inverse of f of x equals 8/3 x minus 8. So it is a function. Last problem on the front has a squared, so keep that in mind. We're going to switch x and y. We're going to move the constant. We need to undo the squaring that happens. So how did we do that in the last problem? How do you unsquare something? You square root. So we have plus or minus square root of x plus 3 equals y plus 4. And if you're going to solve for y, then you need to subtract this 4. So we have y equals -4 plus or minus the square root of x plus 3. Now, what did we see about this last time? We saw that if you graph the positive square root of something and the negative square root of that same radicand, then you end up with a parabola on its side, and it wasn't a function. This is no different. So if you graph this in Desmos, and I don't have it pre-typed in, however, it won't take that long to type in. So I have y equals -4 plus the square root. Where's my square root? There we go. Of x plus 3. And then I'll graph the same thing down here, but I will change my plus to a minus. So look at your graph. Again, a horizontal parabola, not passing the vertical line test, meaning that this inverse is not a function. So when I rewrite it, I just write it as the inverse of y, not the inverse of f of x. So far we figured out how to find the inverse of a table. We've figured out how to find the inverse of an equation. We figured out what an inverse is. It just comes from inverting x and y. And now we're going to move to the graph. So on number 9, the problem says write the equation of the inverse, then graph the following relation and its inverse on the same set of axes. So we're going to graph the relation, the original one, and we're going to graph its inverse on the same graph so that we can see how they look. So first, let's graph the original. The original has a y-intercept or a starting value at 4. So I'm going to go plot that starting value of 4. The slope is 2, or 2 over 1, so I'm going to go up 2 and over 1, rise 2, run 1, rise 2, run 1. I'm going to do the same thing backwards, so down 2, left 1, down 2, left 1. And I'm going to use a straight edge to complete that graph. Now, my next job is to find the inverse, because we wrote the equation, or sorry, we had the equation, we graphed the relation, but now we need to write the equation of the inverse and graph the inverse. So I'm going to switch x and y. I'm going to solve for y so that I can graph this inverse. So I'm going to move the constant. And I'm going to divide everything by 2. I have y equals, this is 1/2 because the x kind of jumps down, 1/2 x minus 4/2 is just 2. And this looks very much to me like it's a function, so I'm going to go ahead and graph the function of x equals 1/2 x minus 2. So my y-intercept is -2. On my y-axis I go plot -2. And then my slope is 1/2, 1/2. So I'm going to rise 1, run 2, rise 1, run 2. Do it backwards. Down 1, left 2, down 1, left 2. And I'm going to complete this with a straight edge. So we wrote the equation, here it is. We graphed the original relation and we graphed its inverse. So is the relation on number 9 a function? Is this a function? Absolutely, it's a linear function. Is its inverse a function? Absolutely, it's also a linear function. And you'll notice that when you have the purple and the pink graph, the original relation and the inverse, what it is a reflection over that parent function, y equals x. Perfect. All right, let's try number 10. Number 10 has the same set of instructions. We're going to graph this equation, which happens to be the parent function, but just +1, so shifted up 1. That's a vertical shift by 1. So I'm going to plot my new y-intercept. Instead of at the origin, it's at 0, 1. I'm going to use my quadratic pattern to find the rest of the points. So over 1 up 1, over 1 up 1, 2, 3, over 1 up 1, 2, 3, 4, 5. Same thing on the other side. Over 1 up 1, over 1 up 3, over 1 up 5. Now, if you're going to write the equation of the inverse, what do you do with x and y? You switch. What do you do with the +1? You subtract. And how do you unsquare y? You square root. So we have y equals plus or minus the square root of x minus 1. We know from previous problems that something like this is not a function, so we just call it the inverse of y. We don't call it the inverse of f of x. It's not a function. Now, you have a couple of options whenever you graph this. You can either make yourself a table, or knowing that the inverse is a reflection over the line y equals x, you can just reflect the points over this line y equals x. So I'm going to show you how to do that. Now, we're going to count diagonally across this dotted line. So from here to the dotted line, it's just like half a diagonal, and another half lands right here. Same thing with this point. From here to the dotted line is half a diagonal. So if we go past it another half, here's my point. Right here, I go 1.5 diagonals. So a half and another 1 diagonal is right here. This point, perhaps I should zoom in a